Good evening, y'all. Welcome back to another Electronics Bash Fundamentals of Arduino. This time on a Monday night. How novel. It's so strange. After 16 Sunday nights, I didn't expect it, but it's a little weird to be doing one of these on a Monday night. I don't know how it is for y'all, but for me, it's a little bit strange. We're gonna, as always, give folks just a few minutes to catch up if they're straggling, before we dive into our topic for tonight, which is hardware interrupts. And we'll get to what that is in just a little bit. But first, I just wanted to hope that all of y'all had a safe 4th of July weekend. No hands or limbs disfigured. Hi, Chris. Happy Monday. Happy fake Sunday. I mean, you know, for a lot of us, what is time anymore? But, you know, it is still a little bit weird in my weekly rhythm that we've built up over the past, 4 months or so. But yeah, it should be good. I hope you all had a good and safe weekend. I hope you had a nice socially distanced weekend. I hope you had some good drinks and some cool shade and some nice sunshine. Me and the wife Mary and the dog escaped to the deep suburbs outside Chicago because while I love fireworks and Mary loves fireworks, our dog does not love fireworks. And I felt last time I felt I should have showed you a picture because she's just the sweetest dog in the world. We've only had her since February, so she's now known more time with both of us at home 24/7 than she has when we used to, go to work. So she is not a huge fan of anything new in her life, like, I don't know, big booms popping up in the middle of the night. So we escaped to the suburbs, had a lovely time in a secret, well-sanitized Airbnb. Now we're back home on a Monday night. So thanks for the adjustment in time. I'm sure it's... who knows if it matters to anybody. But yes. Chris, time to have it interrupted. Yes, Mary and I were just taking bets on, how many interrupt jokes we would have tonight. And it turns out, right now, we're averaging at least, 1 per 3 minutes. So that's a pretty good run, huh? But yeah, keep them coming. We'll have a good old time. Oh, I should say, tonight, I'm mixing it up a little bit. I'm drinking from a can, but I am drinking, let's see, where can I show you? That's way zoomed in. I am drinking grapefruit city water, and not just regular old Chicago city water. This is actually a hard seltzer from Solemn Oath Brewery, who happens to have a little brewery out in Lisle, Illinois, where we spent the weekend. And their hard seltzer is actually really tasty. So, drink local. And hard seltzer seems to be the thing of the summer. I know we've had 16 weeks of beer. Naperville, sorry, not Lisle. It's probably in Naperville. Lisle's tiny. Lisle's where the giant arboretum in our neck of the world is. Naper Thrill. Yeah, not a terribly, rock and roll town, but a good, if you want a quiet place to get away, Naperville, Lisle, lovely places to be. So that's what are y'all, Chris, what are you drinking tonight? Are you having some tasty refreshment? Ooh, I didn't build my mute button this week, which means I'm again reduced to manually muting myself so you don't hear sipping. Chris, I didn't know you grew up in Naperville. I'm sorry if maybe you had a more rock and roll experience of Naperville than I did, but from what I could tell, wasn't a... I mean, we drove through the downtown. It was beautiful. Lots of cool shops, lots of cool things, lots of good stuff to do. Kool-Aid, but switching to anti-hero? Yeah, that sounds like a good 4th of July in Chicago. I can get behind that. Well, since our timer's expired, shall we just get to it? I think I've said this before, I think I have not overcommitted myself to this evening. I'm not saying it'll actually be a 90-minute one, but I think it's not as overwhelmingly too much, as some of the other evenings have been. I think we've broken it up nicely, and I think I already know what we're doing for the next 2 weeks, maybe. But we'll get to that in a little bit. But for now, let's just dive in and talk about hardware interrupts. Or we could just look at my dog all night. That wouldn't be too bad. She's not allowed in the workshop because there's just little bits of wire and stuff everywhere. So I just feel like she wouldn't be super safe in here. But she loves being around people so much. It might be time to do a deep clean of the place and see if she can come and hang out with us for these evenings. All right. But before we get interrupted by the dog, let's talk about hardware interrupts. So tonight, we're talking about hardware interrupts and interrupt service routines, ISRs, which we'll get to in a little bit. We'll talk about making things volatile and what that means. And we're going to have to talk a little bit about the compilation process, which is something we've alluded to a little bit in the past, that the English language version of the code that we essentially write in our IDE isn't what ends up on the Arduino actually getting executed. And there's a series of steps that are, rough form of English in the form of this C program, gets transformed and modified ultimately into a series of ones and zeros that actually go onto the device as code. And we don't, I mean, to be honest, we don't need to know that much about it for tonight to make sense. I just think it's an interesting thing. And it's going to give us, especially when we talk about the volatile qualifier, it's going to make a little bit more sense why that is a useful thing to have. If we understand just a little bit more about what's going on under the hood to turn our C programs into something that actually runs on a microcontroller. So just a little bit of a peek under the covers to look at the compilation process. So let's start with interrupts. An interrupt, very simply, is an interrupt tells the microprocessor to run some other, usually small bit of code right now, right whenever this triggering action happens, whether that's something external to the microcontroller, like a pin going low or high or changing, or sometimes triggered by internal events. Tonight, we're going to be focusing on specifically externally triggered interrupts, because there's a couple more bits and pieces we need to understand before we talk about the internal interrupts, but know that they share a lot of similarities. So here's what I mean by a bit of code running right now. So this code is a bit of gobbledygook. Like this, int x equals 7, then we turn on an LED pin, then y becomes the analog read of this knob we've attached, then byte z is the return value of some other function that we go and do, then this is just a bit of code that you might write. But if for all the code that we've written so far, we would know that we would assign the value of 7 to x, and then immediately after that, the next bit of code that we would run is an LED pin would be set to high, and then the next bit of code would be setting the variable y to the analog read of our knob pin, and so on. With an interrupt, we have the ability to write a function, like say myInterrupt or whatever name we want to call it, and when a certain triggering action occurs, we will jump to that bit of code from wherever we are in the rest of our code. So, for example, we could, and we'll talk about what those triggering actions are, that'll be a good chunk of tonight, and how we set those all up and stuff, but just so you get the vague sense of it, if our interrupt were to be triggered, say, here in our code, right after the analog read, and our interrupt in this case is just turning this LED pin off, setting it low, right? So in this case, we would jump over to the interrupt function, we'd turn the LED off, then we would jump right back to wherever we left our code and move on with the rest of the execution. That could even be in the middle of some other function that we think of as a singular operation, right? And we'll talk about this a little bit more when we look at the compiler and I'll get a little bit under the hood, but things like a delay function, right? This delay 1,000 milliseconds of waiting, right? Which we've used a bunch of times before. We think of it as a single statement of code, but we referred to a few times the fact that under the hood, the microprocessor is treating that actually as a series of thousands and thousands of just do nothing for one clock cycle. The Arduino, as you know, runs at a 16 megahertz, got a 16 megahertz crystal. It can do a thing 16 million times a second. And so a function like delay 1,000 milliseconds is actually setting up, say, hey, for each of, I don't know how the math works out, if it's 1 second, for 16 million of those clock cycles, do nothing. So our interrupt could take place anywhere in the middle of those 16 million things. Like we could be 300 milliseconds through our delay, and then jump over and run our interrupt, and then jump back and do the other 700 milliseconds of our delay, right? That would be the same whether it's a built-in function like delay, a separate function like, this my function that I've made up here. That could be, dozens of lines of code long, but whenever this interrupt is triggered, we immediately jump to the interrupt code, run it, and then jump back to our code wherever we were, even if that's in the middle of what we think of as a singular line of code. A lot of these lines of code are really more than one operation under the hood. And so we will jump back to literally wherever we left off. Sort of makes sense? So why is this a useful thing? Before we talk about how you set one of these up, why would you want to do this? We've talked about lots of structures before that enable us to essentially maintain some multitasking while having a linear flow of code. But things that interrupts are good for might be things like rapidly responding to input. You can imagine, if you're gonna press a button, say some classic. Thanks, Chris. You noticed the SOS? Yeah, bonus points. if you were, where was I? If you're responding to a button press by a user, right? Even the shortest button press is going to be, you know, tens of milliseconds long, which is kind of an eternity when you're talking about 16, you know, million, 60 nanoseconds per clock cycle. A few hundred milliseconds is really easy to detect. But you can think of a really short-lived digital or analog signal coming in. You know, maybe you're trying to catch a transient. Maybe you have a sensor that really needs you to react to it the moment that it goes high. And so the ability for your code to, you know, see that something has changed, jump over and use a function to immediately deal with that piece of input can be a really useful thing. Also dealing with really short-lived events. Maybe you have something that's causing a voltage to spike high for, you know, only a few microseconds. If you're running through that sort of polling loop, that sort of like constantly checking in at various points in your loop whether that thing is high, if you're trying to do other things in your main loop at the same time, you might miss those very short-lived events. Whereas with an interrupt, as soon as that voltage level changes, the Arduino has basically built in hardware that by using some code we can configure to immediately say, okay, as soon as it goes high, you know, within some very small number of nanoseconds, we will jump over to this other code that you told me about, run it, and then pick up where we left off. This is also useful for timing critical events. Like you can imagine, you know, if you're trying to measure the frequency of an incoming signal, by measuring, say, the distance in time between, you know, one rising edge of a waveform and the next. You really want to be able to denotate exactly when the voltage goes from low to high at one point, and exactly as closely as possible when it goes from low to high at another point. And if you're polling, right, if you're just looking occasionally in your loop for when those things have changed, your measurements might be off by a few microseconds to a few milliseconds. What you really want is something that says as soon as that thing changes, then you want to sort of notate the time right now, notate the time right then. You get as precise a measurement as possible. Chris, you never have to worry about interrupting my train of thought. That's sort of the whole point of the night. So especially if there's interrupt jokes, I don't regret those at all. Give me 1 second here. It's really good, this city water. It's not super bitter, which I like. But it's not too sweet either. Huge fan. So various things you could use interrupts for. There's also some like coding style things you can sort of structure your code in a different way using interrupts, and we'll see that in a little bit as well. So come back over here. So like I say, there are two types of interrupts. There's hardware interrupts that are triggered by changes to an external pin, and there are software interrupts triggered by internal counters or timers, or triggered by peripherals. So there are interrupts like when the serial port finishes receiving a new byte, you can trigger an interrupt to handle it. Excuse me, for example. When you have finished writing to the EEPROM, which is sort of the long-term storage inside the Arduino, trigger an interrupt. Especially things that are like things like serial that are happening at 9600 baud if you're running it really slow, or EEPROM writing, which is relatively slow, tens of milliseconds, which in human terms is very very fast. But compared to how fast the microprocessor is running, are relatively slow. And so some of these internal things also are set up so that you can say, hey, I'm going to set this process in motion, then I can go and do other things. And when you're done, throw me an interrupt so I can catch, and say, for something like a UART, you might say, okay, take in a byte, out at 9600 baud, like it's really slow. I'm going to go mess with my server. Oh, you have a new byte for me? I'll take that in. I'll stick it on my buffer. Tell me when you have the next one ready. Like I say, for today, we're going to be focusing specifically on hardware interrupts. Though we will be talking about software interrupts in the future. There's just a little bit more groundwork that we need to get there. But the hardware interrupts really are, I think, the more common type of interrupt that we're using in our hobbyist type projects. So, and all of what we're using today will translate to software interrupts in the future. Just a little bit more of an approachable place to start. If you're looking for the full list of interrupts, if you go to the ATmega 32.8 data sheet and go to the, let's see, where's my interrupt vector table? I had this stored earlier and then I got distracted because I got excited about things. Here we go. Interrupt vectors in the ATmega 32.8p. So you can see there's all these various different types. Reset. So the reset interrupt is actually what's triggered when you power on your Arduino or you press the reset button on it. The fact that it does a little bit of setup for you before it runs your code is actually because it's triggering an interrupt on reset. We've got these two primary external interrupts, interrupt external 0 and 1, int 0 and int 1, And then we have these 3 PCInt, these pin change interrupts that we're going to come back to in just a little bit later part of tonight. Those together are our external interrupts. And then I mostly show this list because I think it's interesting if you wanted to go peek at it. Here's a quick peek at like all the various internal interrupts that you can do based on various timers, which are sort of automatic counters. USART, that's our serial port, our reception complete, transmission complete, EEPROM ready, storing the program, various things. So if you wanted to have a poke around and just get inspired about what is in the scope space of possible interrupts, they're all in the datasheet here in the interrupt vector table. It's kind of a fun thing to poke around in. But like I say, we will be focusing on hardware interrupts tonight. So a piece of terminology before we dive in. The code that runs when an interrupt is triggered is called an ISR, an interrupt service routine. So in our example from earlier, let me scroll back here. So this little snippet of code that I made up called my interrupt, that would be our interrupt service routine, our ISR. It just means a method that you write that takes care of the interrupt. That the interrupt happens and says, hey, I need attention. Your function, your interrupt, services that interrupt. It says, hey, I will take care of whatever's happening here. And routine just means function. So when you see ISR in a lot of these things, that just means a function that's responding to an interrupt. The triggering events for external interrupts can be a number of possible things, but whatever our trigger is, I just want to hammer this home. We jump immediately to the ISR. We jump to that function that we've written. We run whatever code is in it, and then we jump right back to wherever we were in the code before. Literally, when we receive an interrupt, the first thing that happens is the Arduino goes, okay, I'm gonna remember exactly where in my program code I am. I'm gonna put that location away. I'm gonna run your code, then I'm gonna go right back to wherever that spot is and pick right up after there. Right? Have I driven that home enough? I think so. I think we've got the concept there. So I think the easiest way to understand what's happening with interrupts is to just take a look at some example code, and then we're gonna pick apart a few things in it so we can understand what's going on. So this will be, and I don't think I said it at the beginning of the night because I always forget to, if you happen to be new here tonight, all of the code that we're looking at in tonight's examples is on the website, jeff.glass/electronicsbash. There's links to all of the previous sessions, as well as the code and the links to the slides that we're looking at tonight, because I know looking at slides on a stream is not necessarily the most helpful, so those are all available for download there, as well as links to one of the libraries that we'll be using later tonight if you want to download it and play along with it. So let's look at some code. This is the interrupts basic example from the website if you're playing along at home. As usual, we'll zoom in a little bit here. That's pretty good. So a really basic piece of code. Nothing should look too strange here. We'll call it a few of the new things as we go along. We'll define a couple of places where we're going to hook up a button and an LED to Arduino to pins 2 and pin 9, respectively. We're going to define this variable called countdown. It'll start at 0, and it's of this new volatile type that I hinted at earlier. It's still an integer, right? We've seen ints before, but I'm also going to say that it is a volatile integer. So put a pin in that. We'll talk about volatile in a little bit. That's the entirety of our top part here. Our setup looks very familiar, right? Our button is going to be defined as an input pull-up type, right? So that button's connected between our pin and ground. Our LED pin is an output, piece of cake. And then we have a new function here called attach interrupt. Takes 3 arguments, and we'll break this down in just a little bit. Digital pin to interrupt is one of the new functions that we'll put in here as the first argument. And we'll give it pin 2, which is in fact our button pin. So in fact, this could be button pin instead of hardwired as 2. We'll give it a name of our function. We'll give it our ISR function. And we have this qualifier called falling. Now I'm going to break this down for you in just a second here, right? But I want to show you the full scope of this really simple interrupt program and run it, and we'll break down how it works. Our loop is really simple. It says analog write LED pin and the value of countdown. So we'll set our LED to whatever our countdown value is. And we see that to start with, it's 0, right? Then we have setting countdown equals maximum of countdown minus 10 and 0, right? So if countdown is, say, 50, then this is, okay, what's bigger? 50 minus 10 is 40. What's bigger, 40 or 0? Oh, it's 40. So countdown is 40. So we went from 50 to 40. Then we go 40 to 30 to 20 to 10. This just says, hey, if it's less than 0, I just want you to stop at 0, right? So set the LED to this value, decrease it by 10, but not below 0, then delay 100, wait 100 milliseconds, right? And then here is our interrupt service routine. Here's our set state function. It's only going to do one thing. It sets that countdown variable to 255. Right? So let's run this code, and then we'll talk through how it works. Upload that. Come over to the table here. Just make sure that that uploads. Hi, Nate. How are you? 24 hours early? Oh, no. I was afraid that would happen. Yes, thank you. I was just saying at the beginning of the night, thank you for everyone's readjustment this weekend. We got our dog out of Dodge, out of the crazy fireworks in Chicago this week, which I think was a really good idea, but I know it screwed with the schedules a little bit. Doing good. Warm. It is warm and humid here, and I miss California. It is sticky out here. So we were just looking at some code that's using an interrupt to do this. We haven't seen what it does yet. If I press the button, we see the LED turns on and then fades out to 0 over about 2.5 seconds, let's say. Right? I press the button and it fades down to 0. So what's happening there? Well, we've said in our loop, right, every time we go through the loop, we're assigning the value of our countdown variable to the brightness, right, to the pulse width modulation value of that LED pin. Countdown goes down by 10 every time we go through that loop, and we wait about 1/10 of a second in between each time. So if countdown starts at 2:55 and goes down by 10 every 1/10 of a second, that's where we get about a 2.5 second fade out, right? And then anytime I press that button, the interrupt that I've attached to my button pin, I have said, hey, when you see an interrupt on this pin, button pin, I want you to call this function, and the change in state that's going to trigger an interrupt is the falling edge, a transition from high to low, right? So let's talk about a few of these topics in detail. So the attach interrupt function, like we said, takes 3 arguments. The first argument is not a digital pin itself. It is an interrupt number, which don't line up with pin numbers. On the Uno, on the Mega, they're all a little bit different, but the recommended way to solve this is that you basically have a function that you give it what digital pin you're using, and it'll supply the interrupt number for you. So rather than saying attach interrupt to pin 3, you say attach the interrupt to the interrupt corresponding to pin 3, which is the result of this digital pin to interrupt function, right? That's all it is. And then this code is so that, like, if you digital pin 2, where my button is hooked up, I think is on interrupt 0 on the Arduino Uno. I'm actually not 100% sure because I have this function that just gives me the correct interrupt number, which is pretty great. The second value that you provide to the attach interrupt function is the name of your ISR, right? The name of your interrupt service routine, just the name of the function that you want called when something happens. So in my case, I said call the set state function. It finds the function called set state and runs whatever's inside of it. And then you have a variety of types of changes that your interrupt can respond to. It could be a rising edge, a transition from a low level to a high level. It can be a falling edge, so a transition from high to low. It can be any change between low and high. At least on the Uno, it's a little different between the various hardwares, but they can respond to just a low level. Whenever that level is low, trigger an interrupt. And if it's still low, the next time we're available to take interrupts, trigger it again, right? So that's the attach interrupt function in a nutshell. So we're saying, hey, I want the interrupt corresponding to my button pin on pin 2. Give me that. I'll call the set state function whenever that pin goes from high to low. And it will. And that lets us do things like something, Chris, I think that you asked about 100 years ago, back in April. I had this memory of somebody asking, it might have been you, it might have been Palmer, asking about, we had this example where you push a button and the LED gets bright and it fades down. What do I want to do if I want it to be able to go back to full brightness with another button push? And I think I said interrupts would be the way to do that, but I'll put a pin in it. And now, 2 months later, here we are. I might also have made that up, but, if not, it makes a pretty decent story. The nice thing about having this in interrupt, you see, right? If I press the button, we go to full intensity, and then we fade down to 0 over those 2.5 seconds. Not a super smooth fade, of course, because we're doing it in big steps. But anytime I press that button, right, whenever the voltage level on this button goes from high to low, we trigger that interrupt again. And because that interrupt is just setting that countdown value back to 255, right? So every time I trigger that interrupt, we are setting basically our LED brightness value back to full and just decreasing it. Now it doesn't matter if I let this dim all the way down to 0 before I trigger it again, or I can just hammer on this thing, and it will always, as every time that the interrupt runs, it will go back to 255. We could make this fade a little smoother if we wanted, right? If I could say countdown equals countdown -1, so we'll decrease it 10 times slower and we'll delay 10 times less, right? If we upload that code. Ooh, Chris, that makes a lot of sense. Yeah, Palmer was working on that clear comm signaling thing. It does sound related, doesn't it? Now let's see. So if I press this, we should have a smoother fade now. Yeah, it's better. But again, anytime I press that button, whether we're at 0 or not, we're just resetting that value back to 255, right? So that is the gist of the attach interrupt function. You tell it what interrupt and which button to respond to, what function to call, and what state change you want the interrupt to be triggered on. This function, this attach interrupts function, is only for there's a little bit of unfortunate nomenclature here. External interrupts are what the ATmega328 calls specifically this kind of interrupt that we're talking about. The others, which are also, in my mind, external interrupts because they happen on, external changes to the device, are called pin change interrupts. In any case, you see these terms like sort of messed up a little bit. In fact, I'm sure I'm doing it too. But regardless, it's important to know that this kind of interrupt that we're talking about, the number that you get is going to vary based on what your actual hardware is. On the Arduino Uno with the ATmega328, you only have this kind of interrupt capability on pins 2 and 3, right? You only get 2 hardware interrupts. I want to say the Mega has 4 or 6. The SAMD51 variants have like 5. And they're always on specific connection points because basically there's hardware inside the microcontroller that is set up to monitor the states of these pins and trigger the code in a specific way. And it's not something you generally have access to. Hi, Palmer. Palmer, I hope we're not interrupting anything. Point to me. I think I deserve a sip of seltzer for that. Palmer, loop me into this interrupt stuff. I missed it. Oh, it's so good. It's so good. Y'all are great. Okay. So these external interrupts, right? These things we can use to jump around, you only have them on digital pins 2 and 3. We have options for connecting interrupts to other pins, but I'll get to that in just a little bit. So other things we wanted to talk about with this sample code. Oh yeah, so a little diversion into the 2 different types of interrupts, right? This is our big Arduino Uno pinout sheet. Everyone's made their own version of the Arduino Uno pinout. There's lots of them all over the web. This is one that I like because it has a lot of different things on it. It's also one I don't use a ton. I think I still have the one from the very first slides. Oh yeah. This is a much more approachable pinout, right? Because there's fewer things. But as we get deeper into the weeds here in week 16, it's kind of fun to have the full pinout. I don't think it's even full, but just has more stuff on it. But if we zoom in on the right side here, we'll see that digital pins 2 and 3 are denoted int0 and int1. Those are our 2 primary interrupt pins. But that every digital pin and these analog pins up here have this PC int designated next to them. That's because, any of the pins can have what's called a pin change interrupt attached to them. So, like I say, the nomenclature is a little bit stinky there, but for now, we are talking specifically about external interrupts on pins 2 or 3. So let's go back real quick. So we were working our way through our example code here. We talked about attach interrupt and digital pin to interrupt, right? Let's talk a little about the ISR itself, the function that we've written to respond to this interrupt, right? So some things about ISRs. They cannot take arguments, right? An argument, you recall, is any value that we hand to a function to run. So in this example, right, the values button pin and input pullup are arguments to the function pin mode. If I write my own function, like a function called add two numbers, and I takes an integer called a, an integer called b, and it returns a plus b, for example, for the world's most boring function, right? Int a and int b are the arguments to my function called add two numbers. It means the values that we're throwing into our function here. An ISR cannot take arguments. Sort of by definition, it is sort of jumped into naked and blind, right? It says, hey, whenever, we could be anywhere in our code, anything could be happening, could be any values anywhere. We cannot take any arguments in our ISRs. They also cannot return values because, well, there's really nowhere for them to return values to, right? If we go back to our very first early example, right? We could be jumping to our ISR from anywhere in our code. So there's really no way to know what part of the code to hand a value back to. That doesn't mean you can't extract data from an ISR, right? You can change variables. And like we saw, where's our example? Here we go. Like we saw in our set state example here, right? I changed the variable countdown within my ISR, but I couldn't say, countdown, or, int new value equals 255, return new value. That would not be allowed. Actually, I think if I compile this, it'll compile fine. Oh, returns is not a word. Return. I think it'll compile fine, but it won't really do much. This return won't go anywhere. So you can modify variables, but you can't directly return a value from an ISR. Here's an important note. Nothing else is running during your ISR. While your interrupt is running, sort of by definition, the rest of your code isn't. So if you have other code that is timing sensitive, or is currently being pulled or looking for something, that code cannot run because your ISR is running. And so the key thing to do in writing an interrupt service routine is to keep it short. Really what you want to do is sort of the minimum possible amount of work to accept whatever the external input was, whether to service, say, some incoming serial data and push it somewhere else. A lot of the times you will just see the incoming interrupt is received, a flag is set, sort of a Boolean variable is set to say, hey, a thing happened, and then later in your code, in a less time-sensitive fashion, you can deal with that flag. Let's look at how our existing code, I'm sorry, I feel like this seltzer is creating a little bit more audio excitement in the burps than some of the beers have, but it's really good. So in this case, in our set state function, because our action is fairly simple, I said, let's just modify our variable right in here. But a really common pattern might be to declare a flag like volatile, and I promise we'll talk about volatile in a second here. Volatile boolean bool is button pressed equals false, right? A really common pattern we see when you see your interrupt triggered, you would say is button pressed equals true. And then in our loop, we would have some code that says if is button pressed, then do something. And especially if this doing something is something that's relatively time intensive, like opening up a Wi-Fi connection or, sending a bunch of data over to the EEPROM or something like that. Probably what you want is for your ISR to just read the fact that something happens and sort of put a pin in it. And then later in your loop, a few milliseconds later, we can go ahead and deal with that code. So, this might be in this code here, this might be do something lengthy. And then we would say is button pressed equals false. We'd sort of reset our flag here, if you will. A flag is just a word for sort of a one bit of information, a true or false value, usually held as a single bit, a 1 or a 0, just a way of saying, hey, this is happening or this is not happening, or this should happen or this should not. So if I say flag, just think Boolean, a single bit, a 1 or a 0. I like this example that I've sort of made up on the spot here because it has a problem that's a little bit subtle. So I'm gonna save this example for later. I want to come back to it and we'll see if we can pick it apart a little bit. So ISRs, right? You basically are either doing some small manipulation of some internal variables, or maybe just setting like a true or false value so that somewhere later in your loop you can sort of poll for that true or false value, see if you need to take some action, but you're going to capture that input because the interrupt responded very quickly to whatever changed. Here's an important note. So on the same vein as, and I'll get back to that spreadsheet in a second there, in the same vein as no other code can run while your interrupt service routine is running, right? So your main loop, your other functions, right? We've jumped to this ISR and no other code's going to run until it's done. That includes other interrupts. And there's a surprising amount of the stuff that we sort of have used as common libraries and functionalities that actually depends on interrupts itself, like other hardware interrupts, right? If you have an interrupt on pin 2 and on pin 3, which would have different ISRs, if your pin 2 interrupt is running, your pin 3 interrupt cannot run. The delay function that we use so much relies on interrupts to run, so you cannot use the delay function in an ISR. millis and micros do not update in the middle of an interrupt service routine. They will still return a value. You can still, at the beginning of your ISR, and I have an example about this, I think in just a second here. Basically, at the beginning of your interrupt, one thing you might want to do is say, okay, well, what's our time in milliseconds since the program started, or the time in microseconds, right? You can still call those functions, but they aren't actually updating because the programming behind them requires interrupts to work, so they sort of stop counting ahead. I've also seen reference to, and I haven't really explored this yet, that the micros function in an ISR returns accurate values for the first couple milliseconds and then starts to sort of give gibberish. I saw this note sort of like 2 hours ago as I was looking through some more documentation this evening. Maybe beware of micros used in interrupt service routines, but that can be for someone else to go and explore. A few other things that require ISRs, the tone function that puts out musical tones, the servo function, right, that's sort of outputting a variable sized pulse width to control the position of a servo, analog write, like a pulse width modulation function. All those things are using interrupts internally to generate those various waveforms, and they cannot be triggered until your ISR is done, right? Which is another good reason to keep your interrupt service routine short, right? With our very simple example here, we basically have one variable changing. This is going to take a very small amount of time to run. And so even though my tone function can't update for, the few hundred nanoseconds while we're dealing with this routine, to the human ear who's looking for something, changing at 400 hertz, right? So changing every few milliseconds, a few nanoseconds of delay in how long we're taking to update those functions, we're never going to notice. So as long as we keep things short, these things are fine. I can also, in any of these ISRs, I can still write the functions. I can still see, analog write, LED pin 120 or whatever. I can still use those functions. It's just that the actual sort of hardware behind what's actually changing those values isn't being updated, and won't be updated until we sort of return from this ISR. The one that really gets you in trouble is delay, right? So if I say in my ISR, in my service routine, if I say wait for a second, which I would never want to do in an ISR. The whole point is to keep them really nice and short and compact, so we can get back to doing other things with our code. But let's say I did this, because the programming behind the delay function is using other interrupts to sort of count up to 1,000 milliseconds in this case, but that other hardware is interrupt based and can't run while I'm already servicing an interrupt, this will hang forever. This will basically say, okay, I'm gonna wait until I've counted to 1,000. Timer, you give me pulses and let me count to 1,000. The timer says, I'm not counting anything. We're doing this other interrupt thing over here. And nothing ever happens again. So beware of delay in ISR. I mean, beware of delay in general, as we talked about, but just some things to know. All right. Oops. I closed my slides. Well, that's not going to be super helpful. Let's see here. So that is the gist of the ISR. Oh yeah. So let's look at another example. This is I sneak in a little Arduino Uno in the corner here to remind me to go do some demos when they come up in the slides. So we talked a little about flags, and one example I want to show, let's see here. Do I have a good example for this? I might actually not have a great example. Oh, but I do have one that's going to show a related point. This is the interrupt serial example if you're playing along at home. Same setup as before, a button on pin 2, an LED on pin 9, a volatile integer called counter. I swear we're going to talk about volatile in just a second here. In our setup, we have an input pull-up type for our button pin. Our LED is an output. We'll start our serial console here. And much like before, we're going to attach an interrupt to that button, call this set state function, and it'll trigger on a falling edge. And all it's going to do is say, every time I go through the loop, I'm going to print the value of my count variable, which remember starts at 0. So print it out and then wait a second. So basically, once a second, print me out the value of this variable count. And then my interrupt service routine here just is going to increment that by 1. So we'll basically be printing out a count of how many total times the interrupt has been triggered in our program, right? So let's upload that, take a look at it. I think the LED actually doesn't do much here, so there's not gonna be a ton to look at. So let's keep it over here on the computer, and I will open up my serial monitor. Oh, it's gonna do this weird thing again where I can't get at the whole thing. That's so strange. Change my baud rate and I'll shrink it back down there. So you can see our count starts at 0, right? We haven't triggered the interrupt at all. If I come over here and I press this button, we'll see we triggered the interrupt once, click twice, click 3, 4, and so on, right? We basically get a count of how many times we triggered the interrupt, except that sometimes it counts up by more than 1. I swear I didn't press the button, what is that, 12 times in that singular second? But the count on that interrupt jumped up by a lot more than the number of times I pressed this button. So a couple presses in a second, and we can still see what we're counting during that delay. We sort of dodged that problem we were having with delay that no code could run. But we're sometimes getting multiple increments per button press. And that's because of this debouncing problem that we've encountered before, that the two contacts, the two copper contacts, yeah, exactly, Chris, it's debounce, right? Those two copper contacts are, instead of making a solid contact and a solid release, when they come down, they bounce a little bit. We get a falling edge, rising edge, falling edge, rising edge as these things settle into place. So it's not uncommon within an ISR structure to use a little bit of debouncing code as well. Debouncing just means to say, all right, if my contacts are going to do this for a couple of milliseconds, say, I'm going to accept this first one as an actual input, and then I'm going to ignore the rest of these for a certain amount of time, because I assume they're not Jeff hammering on this button 500 times a second. I'm going to assume that's just those copper contacts slapping about. So we have another example here. This is the interrupt serial debounce example if you're playing along at home. This looks a lot like debouncing code that we've used before, if you remember from week 2, 3? How long ago was that? All we've done is added a couple of variables here, which will hold that the last time that we incremented our count and the minimum amount of time between button presses in milliseconds. In this case, it's 100 milliseconds. I don't think I'm going to want to press this button more than 10 times a second, let's say. And then in my ISR, right, all this other setup is the same, right? I'm attaching the set state interrupt to pin 2 on a falling edge. And then in my ISR, I'm just going to say if the current time is greater than the last time I press the button plus the minimum amount of time I have to wait, then do some things, including, well, it is now currently the last time I press the button, and increment the count by 1. So you notice I did this example mostly to say, so I am using the millis function within my ISR. It's just that in a normal bit of code, say if this is my loop, this millis and this millis might be incremented, say, a couple of milliseconds apart. But by definition, inside an ISR, the millis function isn't incrementing, so these two will end up being exactly the same. Now, for my purposes, that's fine, but you can't, say, use a single interrupt to, record the time in millis, do a bunch of things, then get the time again and see how long your internals took, because millis is not sort of increasing, not tracking time within your interrupt service routine. So this is a pretty common debounce pattern to say, if the current time is beyond the gap of time since my last actual event happened, well, then remember the current time is the new previous event and then take some action, right? So if we open up our serial terminal here, let's see, Chris has a question here. I just want to show you this example, and I think Chris has a really important question. I just want to show you that now, even if I hammer on the button, I can't press this 10 times a second, but each time I do press it, I get a single increment of the counter. If I press it 2 times within a delay, I still get an updated count. Chris's question is, so what's the advantage of using interrupts for this example instead of just using if the button is pressed, then count? So the advantage here, Chris, is it goes, oh, we're over here. The advantage here, Chris, the advantage over here, and not over here, is that we can be doing other things in the meantime. I've sort of railed against the delay function as like it just wastes time, right? It's like it's not doing anything, you can't do anything else. You can have an interrupt you in the middle of a delay function. So in some sense, right, one advantage, and it's a small one, is that like this is a cleaner way to write this function rather than our usual sort of check if the baby needs checking on function, if our millis and previous time function sort of setup that we've talked about before. The other advantage is like, what if this delay, instead of doing nothing, was representing, say, a bunch of other code that needed time to run? Like, what if this was, say, here's a practical example, and I didn't put this together to show you, but it would be a good one. I have a little ultrasonic distance sensor I've been playing with that basically sends out a pulse of sound that reflects off of an object, comes back to the sensor, and that tells it something about how far away the nearest object is, right? To take an accurate sensor reading with that, you want to do that a few times, and so to get the distance to an object takes a couple hundred milliseconds at least, right? Which is, for the purposes I'm playing with it for, that's fine, right? 5 updates a second is plenty, but it really needs to be focused on absorbing readings from that sensor at all times. It's like I had a delay 200 statement in my code every time I look for a reading from that sensor, right? But I also want to, take a little bit of input, in my case, from like a little tactile switch. So as long as I can put that in an interrupt and know that like whenever I push that button, I can trigger a little bit of code to run. Now, that little bit of code, yes, is running in the middle of my sort of sensor absorbed code, right? So I am looking away briefly to go address this other thing happening. So it's not solely functioning on the sensor all the time. But you can think of processes that really make a lot more sense to process linearly, like let's say I had a bunch of nested for loops, right? Int I equals 1, 0, I is less than 100, I plus plus, and then this a little bit is going to look like, I'm making this up a little bit, but this kind of looks like our snake game example, where we sort of had to process a bunch of individual spots on a board and sort of analyze them every step we took through the game. Once you start doing these sort of like, if I have 100 by 100 grid of, say, NeoPixel LEDs, I have to update as frequently as possible, right? And they all take some amount of thinking to do in the middle. Suddenly, I'm sort of spending a lot of time in each loop taking care of other things. By sort of setting up my interactivity code as an interrupt, I know that whenever it happens, I can step away even in the middle of a loop, even in the middle of whatever this process is in the middle, service my interrupt, sort of remember that I'm handling a button input or something like that, and then I can jump back to my code. In that case, that might be something like, that might go back to our sort of flagging example. I might say, if is button pressed, then do something, right? In the case where I have to process a bunch of outputs and then maybe respond to some input, it might be more important just to remember that, like, hey, the user pressed a button sometime while I was in the middle of this loop, and once I'm done with all of that, then I'll get around to dealing with it later, so I can keep this ISR nice and short. But I know I'm not going to miss that button input, even if this sort of intermediate code takes a long time. Does that sort of make sense? That's one of the purposes of an ISR is, even if your other processes are taking a significant amount of time, you aren't going to miss an event happening. Excellent. I will totally say, this is a very basic example, and like, of course, with a blinking LED or a button input, like you could totally do this in a pulled loop kind of way. Just sort of a building block for more interactivity for sure. Let's see. Yeah, so like I said, so ISRs, if you're doing, changing a variable or two, you can do it right in your service routine. Otherwise, it's more common to just throw up a flag, set a Boolean value, and say, hey, I'm going to deal with this at an appropriate point in my code. Let's get to that qualifier volatile that I referenced there a little bit. So we talked about, I think in passing a few weeks back, the const modifier that I've used actually a little bit in this code here, I'm realizing. Const int button pin is 2, const int LED pin equals 9. The const qualifier, right? Basically an adjective describing this integer. Const means this thing is never going to change throughout the entirety of my program. So we don't have to worry about having any code that's going to say that this is ever going to be something other than 2. We can treat the symbol button pin as being equivalent to 2 in all cases, right? So const is a qualifier that does that. The volatile qualifier also modifies a variable type, so it might have a volatile int, a volatile bool, a volatile long, and so on, right? The volatile modifier tells the compiler that a variable may be changed by out-of-sequence actions. So what do all those words mean, right? Now this is the getting under the hood part of what it means to work with ISRs and the volatile qualifier. The compiler will always read the value from memory rather than a temp register, right? That's just more words. Let's talk about what that actually means, right? Up until now, right, if we go back to our very first example of the night, we could always be certain before we introduce interrupts into the mix that if we in this case, say int x equals 7, digital write LED pin equals high, these two statements will always follow each other. In fact, if I were to write some code like, I'll just start some new code, in our setup code here, int x equals high, digital write, let's say pin 13x, right? Some really basic code. Now, because this code is in order here, right, we know that x is high, and the next bit of code that we're going to run is this line. So this could just as easily be replaced with digital write pin 13 high, right? That sort of makes sense. And in some ways, that's going to be a slightly faster bit of code to run. This is going to have to sort of create a variable, which we know from a couple weeks ago is 2 bytes long, find a place in memory to store it, store a value in it, and then the next line we pull that value back out and use it to do this digital write function, right? In some sense, this, where we sort of do things directly, is going to be faster. And we can see that as humans, right? We know that this line is always going to follow this line, so these two things are basically equivalent. In fact, let me write them as 2 separate examples here. Digital write 13 high, right? So these two very simple artificial examples here are basically the same thing, right? Under the hood, our process that translate our C code, our English here, into ones and zeros that can be run on the Arduino can see this as well, right? It's going to try and condense all of this logic as much as it can so the code runs as fast as possible. Here, let me come back to my slide here. Go. So in this case, right, I don't think it's actually baked into this. Oh, here, I baked into this function, right? I said int x equals high, digital write LED pin x, right? This is basically the same as writing digital write LED pin high. There might be cases where it is not necessarily certain what the value of a variable is going to be before the next line, like int y is analog read of our fictitious knob here. Byte z is the function value applied to our variable y. Well, since we don't know what y is going to be, since it depends on some physical parameters, we can't quite collapse this one as much, right? Like, we don't know what y will be until we run the program. But this, in this case, the integer x is basically redundant. It's just a stand-in for high, and any smart compiler is going to be able to collapse that for us, right? So here's another way of looking at it. Inside my dumb function, that's right. I wrote these examples last week, and I'd forgotten a little bit of what I had made them for, and they're kind of a gift to future me now, which is a lot of fun. So here's a function called dumb function. Sets the integer a is equal to 1, says if a is 1, return true, otherwise return false. This is basically the same as true. Right? This function will always be true. A is 1, and if a is 1, then true, right? Very simple. This is only true, though, in the case that we don't have interrupts in the mix, because, like we now know, interrupts can run any time, right? An interrupt could change the value of a here. If I had an interrupt that came in and said, if I press this button, set a to 0, and then if a was 0, we'd return false. So we shouldn't be allowed to collapse this function in the same way. The way that we tell our computer that the variable a could change at any time, might be changed by an interrupt, is to use this volatile qualifier. Volatile says, hey, this variable, listen, you can see in your code where you think it's going to change, but I'm messing with it in interrupts. Don't ever make some assumptions from one line to the next that something might not have happened to it in between, right? So in this case, we're not going to sort of optimize out and sort of just, return true all the time. In this case, if we make a volatile variable, we're going to always, we actually will take a variable name, assign it a value, and then hopefully right after do this comparison and return true or false. But we will always genuinely do that comparison. This goes back to that jumble of words I started with. The compiler will always read the value from memory rather than a temporary register. It says like, hey, don't try and get clever with a equals 1 and if a equals 1. Just actually do this thing. Don't make any assumptions line to line, because I know in the background I'm messing with things in between lines. That sort of makes sense? So that sort of makes sense. That's kind of an important point about volatile and what is actually happening with the interrupt service routines. I'm gonna take a sip and then I want to get into just a little bit of a nerd tangent. But since we're less than an hour in and we're actually moving pretty well, I feel pretty good about nerd tangents tonight. this was a solid choice. It was been a very, very hot and sticky day here in Chicago, and these are so refreshing. I don't know that city water is necessarily the name I would have chosen. I don't think it has a great connotation, but I don't know. I like our city water, so I guess there you go. So I've been tossing around this term compiler a little bit tonight, and I wanted to just briefly allude to and sort of spell out in just a little bit more detail. Hi, Rufus Doofus. I'm not Rufus Doofus. I don't know that I've seen you here before. I'm good. Well, but you're ready for a nerd tangent. So you are exactly the target audience for these things, and I'm stoked. I've been tossing around this term compiler, right? The compiler is going to do this. The compiler is going to do that. Compiler with the variable tells the compiler that the variable may be changed by out of sequence actions. A compiler will always read the value. What the heck is the compiler? Well, I wanted to outline just briefly. Let's step back through the slides here. Slide. What the process is that turns what we write in the Arduino IDE into the actual ones and zeros that live in the memory of the Arduino, right? So this is a really broad strokes overview, and there are some links in the last slide of tonight. And again, those slides are on jeff.glass/the-electronics-bash. Down the slides, there's 5 or 6 links, and one of them is a much more detailed version of what I'm going to talk about in one slide here. So kind of a fun read if you're interested. We start with our sketch files, right? And for our point, that's literally just, the file or files that make up your sketch in an IDE. We haven't really messed with any multi-file options, but this tab up here at the top, which has your file name, you can break up your sketch into multiple tabs if it gets long enough, right? We take all of those, put them together, and those make up our sketch files. When we hit the compile or the upload button, the first thing that happens is the Arduino IDE runs what's called the pre-processing program on it to turn our sketch into something that's actually a little bit more properly a C++ program. There are some things that you would need to do to write a valid C or C++ program that the Arduino IDE just kind of takes care of for us. Things like, if you're looking at C code, you'll notice a lot of times you'll have a file called interrupt demo.h and .c, one of which has what's called function prototypes, which is the name of a function before you can actually write the function. Anyway, all this happens in the background for you because it's, a little bit cumbersome. And the whole point of the Arduino and the wiring process is to make these things sort of as low friction as possible, right? But just know that under the hood, it's doing a few more things for us. It's also, when we use those include statements to bring libraries into our code, this is a step that says, okay, let me go actually find those libraries, grab the code from them, and so on. Bring those all together into one big program, right? The preprocessor basically turns what looks like C code to us and turns it into more proper, formal C code. Palmer, I don't know that everything you write is sketch, but I certainly have seen some of the things that we built together, and there's just a little bit sketch. So once we have our C++ program, this is the point where the compiler comes in. In our case, in the Arduino IDE, it's called the AVR GCC is the name of the program. AVR is the shorthand for the manufacturer, the Atmel manufacturer of these chips. GCC is the GNU C compiler. It's just a compiler for the language C. And AVR GCC is the variant of that that's made for AVR microcontrollers. Compiled code is essentially the version of our C language construct that is broken down into steps that a microprocessor can actually do and understand, right? So the microprocessor itself, the ATmega328 on my bench here, doesn't know anything about analog write, but it knows how to, move a byte from here to here. It knows how to add 2 bytes together. It knows how to subtract 2 bytes. It knows that if it has a byte in this position, then the first bit of that byte represents whether that pin 1 is an input or an output, and the next bit is whether pin 2 is an input or an output, and so on. It has basically a much more basic understanding of how the things actually work. And so it's the job of the compiler to turn our English language, our C++ program, into these very simple statements about bits and bytes that the microprocessor can run. So it's a fairly advanced program. And the AVR variant of GCC is to basically make C code that will run on an Atmel microcontroller. If you were, say, running a C++ program on your desktop, you would need a different version of GCC. And you would need different variants of it based on whether you're on a Mac, on Windows, on Linux, on what have you. So this is the step. This is when I say that the compiler, does some optimization, this is the point in turning our English language words into these very fundamental instructions. That's the point when we might be able to see things like, hey, I have a statement that sets a variable and then immediately after reads the value of that variable. I'm going to take those two statements and sort of condense them into one. That's what the compiler, in this case AVR GCC, does for us. A couple more steps that happen after that. AVR GCC also takes care of turning that compiled code into what's called hex code, and that's literally the ones and zeros that will be ported into our device. There's a specific format, and it varies a little bit per which specific processor you're using, so it's sort of a separate step, right? We turn it into these very simple instructions about bits and bytes, and then we say, okay, on this controller, this instruction about move a byte from here to here is represented by this string of ones and zeros, right? So we turn it into hex code, and then finally, we use a program called AVR Dude, I'm not kidding, to actually get those ones and zeros onto the Arduino through the serial port. So that's really, in a broad nutshell, what the build process looks like. But part of the reason I took this tangent is that there is a really cool way of looking under the hood at what's happening here called the Compiler Explorer, which is at godbolts.org. So a lot of people seem to just call this Godbolt. It's nothing like highfalutin. It's just named after Matthew Godbolt, who built this website and used his own name. Compiler Explorer is what he calls it. A lot of other people just call it Godbolt, which is kind of an amazing name. But what it is basically, here, let me get rid of that for a second and just zoom in on some code here. This is a really cool place to play around if you're a nerd, and I'm just gonna make an assumption that you all are. This basically says, hey, write some code on this side, and I will give you the compiled code on the other side, right? For a variety of compilers. So up on the top here, I can select, I want to compile my C code like an ARM CPU with this version code, or like a Windows x86-64 machine, like a Windows compiler, or a MIPS compiler for other operating systems. But partly what's cool is it has the Arduino Uno, at least the 1.8.9 compiler built into it. So we can actually, in a really easy way, look at what that compiled code with that really basic instructions that the Arduino is actually running look like, which I think is really neat. There are ways to have, as you're compiling, have the Arduino IDE spit out the literal assembled code to like a text file for you to look at as well. They require modifying some config files, and it's a little bit cumbersome. If you Google, Arduino IDE output assembly, it will pop right up. This, I think, is the fastest way to look at this. And if you're just interested in like playing around with some of these ideas, I encourage you to try out Godbolt, because it's kind of a fun thing to play around with. But it's going to let me sort of illustrate the difference between a volatile variable and a not volatile variable. So let's see. Right, I've written a little bit of Arduino code here. Oops. And I've messed up the formatting already. So I'm using my Arduino compiler, my Arduino 1.8 compiler. I've included wiring _private.h. This took me a little bit of fiddling around with, so if you're trying this out at home, this is the command, include wiring _private.h. This gives you all of like the Arduino functionality under the hood, because of course, like digital write is not a native C function. But it is a native Arduino function, so by including the sort of basic Arduino functions using this wiring file, you get to, it will still compile if you use all the basic Arduino code, essentially. So what I want to look at here, though, is this really, this may as well be called, I'm going to call this dumb function, because that just gave me a good laugh. Here's my function called dumb function. Now see, it's very similar to the example we were looking at a moment ago. I declare a variable called variable. Again, another example I came up with before we left town, and I was just so creative. Variable equals 1. If variable equals 1, return true, else return false, right? So this should always return true. If I look at the compiled output, here's what I see. And if you want to learn AVR assembly, feel free. It's super fun. I've learned just enough to be able to explain this example. But basically, register 24 here, which is just a specific byte in memory that the Arduino knows where it is, right? It says, I'm going to load a value into register 24, and register 24 is one of the places that, like, return values go. We think of like return values from a function being sort of passed from one function to another. Inside of the code, it's basically saying, okay, by the end of my function, I'll have whatever I want to return in this place I'm calling register 24. We can see that my function called dumb function isn't doing any kind of comparison or assigning a variable anywhere. It's just loading a value of true, in this case 1, into register 24 and returning. That's all dumb function is. Ooh, in fact, if you mouse over, it gives you a little bit of a description of what those functions are, at least for return. Interesting, it doesn't do it for load. So we've optimized out the idea of this variable because the code knows, well, 1 is always going to be equal to 1. I'm not going to run some additional steps. I'm just going to return true. That's all this guy needs. But what happens if I add the volatile keyword in front of my variable here? We see my code got a heck of a lot longer on the compiled side. I now have a couple of places where I am having to remember some variables. And inside my function, I'm doing a variety of things. I love playing around in Godbolt because it also color codes where things are coming from. So we can see that my statement here called volatile function variable is going to be assigning a variable. And then I'm actually doing this comparison. I'm loading a value. I'm doing this comparison instruction. And then I have this branch if equal instruction, which says if these two things are equal, go to this other place. If not, go to this first place. So we can see that by making this a volatile variable, now my code is assuming, okay, well, this is a variable that might be changed by an interrupt in between line 4 and line 5 over here. So I had better treat this as a genuine changeable variable, whereas if it's a non-volatile variable, it's happy to optimize it out as much as it wants. Cool, right? And really clever. Let's see. What other things have I set up to test here? Interrupts 1. Oh, so this is cool. Just as a little final demo of what Godbolt can do for tonight. This is a copy and paste of the interrupts basic code from the beginning of the night, right? This is our button pin is 2, LED pin is 9. This is that countdown function where the LED was set to full every time it ran and then was fading down. And you can see it's broken out for us what all of the various assembly instructions are that's making these things happen, which I think is really cool. So, and I mostly wanted to do, let's see, where is my loop function here? So, the thing about AVR GCC is it's not as heavily optimized for, as it could be, because it assumes that functions can be run a little bit out of order already. So even though, if you didn't know that there was an interrupt coming, you might say, well, countdown is set to 0 at the start of my code, and as far as the program knows, countdown will always be 0, so why am I not just analog writing 0 here? Why am I loading this variable? In AVR GCC, it assumes that, variables may change a little bit. So even without declaring this as volatile, we're seeing that it's still loading the value of that variable and then writing it to this analog write function. But if I do declare it as volatile, let's see what changes. I actually don't remember what happens here. Let's find out. Oops, that's the wrong place to declare it volatile. It's up here. This uint 8t, you'll remember from a few weeks ago, just means byte, right? An 8-bit unsigned integer. Same thing as what we call a byte in Arduino land, right? So not a ton of things have changed, although we will see that down here in our... What is this corresponding to? That's our if. That's in our countdown equals max 10 0 function. So the max function, right, is essentially an if statement in disguise, right? It says if the first thing is bigger, set this variable equal to the first thing, otherwise set it equal to the second thing. Sort of an if statement in fancy clothing, right? So inside of this this max function here, right? If let's take away the volatile first, and we'll see what it looks like, right? We can see the first thing that happens is this orange section here. I did warn you it was going to be a nerd tangent. We're going a little deep, but it's really cool. So when we get to this point, right, where we're going to have to sort of say, if countdown is greater than this thing, do one thing, otherwise do this other thing. We're loading the value of that countdown variable into a register so we can do something with it. And then we're doing a bunch of math on it. And we have another one of these branch instructions, right? That's a point where our program could go to one place or go to another place, right? But we'll see we're only loading the value of that countdown variable just the once at the start of the function. If I declare countdown as a volatile variable and let it recompile, we'll see we're actually loading it twice. We load it in, we do some comparisons, we branch, And then before we do our subtraction, we actually load it from memory again, because the compiler can't assume that that variable hasn't changed in between the two calls to that function. It's volatile. We could have jumped that interrupt in between those two things. So, whenever we need it, we're gonna have to call it up from memory and try again. That is the gist of the volatile function. That is, I think, the end of the nerd tangent into Godbolt. Really, go try copying and pasting some of your Arduino code into it and see what the assembler comes out as. Because it's kind of, I think it's really interesting to see how, things like, how things appear in assembly, and how sort of compactified they can get, and how clever the compiler can be with minimizing variables out of your code. Anyway, thank you for allowing me my nerd tangents. I think are a really fun toy to explore. So we want to use the volatile keyword, right, whenever our variable sort of might be changed by an interrupt service routine. What if you're doing some kind of an update that takes more than one instruction to do? And by instruction, I guess I mean both like one line of code, but also in the compiled sense. What if you had say a long integer, or a variable that took up bytes and bytes of space, like an array or a string, and you wanted to make sure that every time, say, you updated that string, you didn't want to go out to your interrupt service routine and change that string while it was being modified in your code. Let me show you an example. So this will be the interrupt arrays example from the website if you're playing along at home. It's a pretty contrived example just to kind of keep it nice and short and tight. But basically, we'll define an array of 9 zeros called my readings. And then at some point in my loop, I'm going to come through and I'm going to, let's see, how did I do this? Oh, when my interrupt service routine gets called, I'm going to read the value from 9 different digital pins into the readings in my interrupt, into the array, right? I'm going to read from pins, I think, 4, 5, 6, 7, 8, 9, so on, store those in my array, and then later on in my loop, I'm going to do something with those readings. But I want to make sure, whenever I, say, press the button or whatever my trigger is, I want to get all those readings right at once. And then in my loop, I want to, I think in this case I said I want to, if more than a certain value, if more than 5 of them are true, then that represents a trigger function. Maybe these are, temperature sensors all over my building, and if more than 5 of them have tripped, the building's on fire, right? And 5 is my threshold, or something like that, right? So inside of my loop here, I'm going to sort of cycle through my array, and if my reading is true, then increment a count variable. And if my count is bigger than my trigger, I'll say my trigger is on, building's on fire. And if it's not, then we're safe, or something like. I told you, it's a pretty contrived example. But the point is, in the middle of analyzing this array, which I'm doing sort of every time I go through my loop, I don't want my interrupt service routine to trigger and start modifying the variables in my array. I've sort of set this like, whenever I trigger the interrupt, I want to take the readings right then, and they will represent a discrete moment in time. And so when I come back and analyze them, I don't want to be sort of analyzing, comparing the first element of the array and the second, and then have my interrupt trigger take another set of samples, change my array, and then continue, right? I jump back to my code. I started to compare my array at position 3, position 4, position 5, and so on. I want to be sort of comparing the whole thing as a chunk. This would be true if it was numbers, if it was working with strings, lots of other things. So one thing you can do is temporarily disable interrupts. And the Arduino IDE gives you some really simple functions to do it. You get this no interrupts and interrupts function. No interrupts just turns interrupts off temporarily. You can do your bit of processing that you want to sort of treat as an uninterrupted process, and then you can turn your interrupts back on. This no interrupts and interrupts function only affect the user-defined interrupts, this sort of attach interrupt function style. It doesn't mess with servo, millis, all that stuff. It's just for things that you have defined yourself, if that makes sense. I also want to point out, I put it in the comments here, in the C code, in the sort of more native C code that AVR GCC is looking for, the no interrupt function is called the CLI function, the clear interrupt flag, and the interrupts function, the enable interrupts, is SEI, the set interrupts flag. I wanted to mention that because in a lot of examples that I saw over the internet as I was sort of casting around for this session, Rather than seeing no interrupts and interrupts, you see CLI and SEI. Same exact thing. Literally, no interrupts is an alias for CLI and so on. But I wanted to call that out because you're more likely, I think, to see CLI and SEI than no interrupts and interrupts. I think because these were added in a more recent version of the Arduino IDE. Same exact thing. So that's a way if you want sort of interactions to happen on your data in a way that your data can't be interrupted, so to speak, in the middle of its processing, you can use that no interrupts and interrupts function to temporarily turn them on or off. Questions while I take a sip? As always, the lag makes it complicated, but I assume you'll ask them. While I figure out where I was. Oh yeah, we were just talking about, here we are. Talking about, volatile. If you're updating a variable longer than an integer, that's sort of our cutoff. Like if you have a string, if you have an array, and you want to sort of update it all at once, you can disable interrupts in your loop function to sort of keep your variables safe while you're working with them, and then enable interrupts again. Now, of course, there is the possibility, right, within that code that, during this bit of time while I'm processing this array, my interrupt could have been, triggered, and not seen, so to speak, right? In this case, I think I was using my button again. My button has a falling edge trigger my interrupt. What will happen in that case, if you have attached an interrupt to a pin and temporarily disabled it, basically the fact that there should have been an interrupt will be stored in the Arduino, and when you re-enable interrupts afterward, it will still get called. So in this case, right, let's say I'm in the middle of processing my array here, I press my button, I trigger my interrupt, it's not going to do anything right away, but the flag in memory that says, hey, that interrupt was triggered, will still be stored. And so when I finally get around to sort of re-enabling interrupts, it'll say, okay, I'm going to run through my list of interrupts that I should see. Have I reset recently? I hope not. External interrupt 0, no. External interrupt 1, I should have run this. I'll run it right now, right? So it's not that it necessarily will get missed. It's just that it will run later, if that sort of makes sense. What's next? Oh, yeah, so that's the gist of external interrupts. I want to talk briefly about pin change interrupts. This goes back to our Arduino Uno pinout that we have here. When I referenced earlier that int0 and int1 are connected to digital pins 2 and 3, but we have all these other PC interrupts. Basically, every pin is pretty much a PC interrupt. That is a pin change interrupt. They are fairly more limited than our external interrupts, but they're worth talking about. An important thing to note on this datasheet too is that while the Arduino environment refers to our various digital and analog pins by nice clean names, 0, 1, 2, 3, A1, A2, nice familiar names, internal to the processor, they are referred to by port number. There are three external ports on the ATmega 32.8. Port B, C, and D, and each one represents a number of pins attached to the outside of the Arduino. So, for example, digital pin 0, what we would call digital pin 0, internally is referred to as port D0. D1, D2, D3, and so on. Digital pin 8, 9, 10 are port B0, 1, 2, 3, 4, 5. What we call the analog pins are on port C, and so on. There is no port A on the ATmega 32.8. I did a little digging, and it seems like there's mixed answers as to why that is. The most common is that the 32.8 is sort of a chopped down version of another processor that did have a port A, and when they developed the 32.8, they sort of lopped off that port, but didn't want to change the naming scheme so all the code would still work the same. So you have ports B, C, and D. There is no port A. So important to know that these pins have an internal name to them and sort of organized into these three ports, because for a pin change interrupt, you basically get one ISR, one service routine, not per pin, but per port, right? So on pin 2 and pin 3, we could have two separate interrupts. We basically get one interrupt for all of port 8, one for all of port D, one for all of port B, one for all of port C. You can configure which pins on that port trigger the interrupt. So for example, let's look at port B here, which you can see is digital pins 8, 9, 10, 11, 12, 13, right? I could say that only pins 8, 9, and 10 trigger a pin change interrupt, but whenever any of them is triggered, they will trigger the same function, if that sort of makes sense. They also can only trigger, a pin change interrupt can only trigger on a pin change, whereas our external interrupts, right, we said, well, it's a lot of slides to go back through, we could define our interrupts as rising or falling edge, or anytime they changed, or just sitting low. For a pin change interrupt, as I scroll back through all the slides, we can only trigger on a pin change. So they're a lot less versatile than an external interrupt would be. The other thing about pin change interrupts, and the reason that I put them second, even though they are sort of attached to more pins, in addition to being less powerful, they aren't really encapsulated, by any decent libraries that I know of. Partly because their operation is sort of so tied into the hardware that it would be a little bit cumbersome to wrap them up in a library. So the way that you would configure them is using some sort of direct math on the registers of the Arduino. And a register, and I think I mentioned this earlier tonight in passing, is basically just a byte in memory that means something to the operation of the Arduino itself, right? So, for example, and this is not the point of tonight, but like, the PC mask 0 is for like the pin change mask for the register 0 interrupt says which pins should be associated with this particular PC, this particular pin change interrupt are represented by these 8 bits here, and so on. A register is basically just a byte memory that means something other than data or program. It actually controls the behavior of the Arduino in some way. And because these pin change interrupts are sort of so closely tied to the hardware, this is really the best way to configure them. And it's a little bit, there's stuff to tease apart here, right? This is not the most immediately parsable, I would say. So registers and register math, binary math, and bitwise math is going to be one of our topics for next week. We're not done tonight. Don't go away. But this is why I'm going to put a little pin in pin change interrupts. Well, there's more to come on that too, until we talk about register math. Because as I started to plot out this week, I was like, well, we could talk about like all these various bitwise operations and how you interact with registers, but that should be a whole night in and of itself. And for once, I was smart and didn't get in over my head, I think. But that said, there is something I want to call your attention to, which is a really nifty library called Enable Interrupt. You will sometimes see, if you're looking for information, there we are, on interrupts online, there's an older library called Pin Change Interrupt, the library. It's not quite as full featured, it's a little bit slower. This new one, called Enable Interrupt, which is linked in the last slide of the slides or on the website, is really neat. It basically enables software-defined interrupts using these pin changes. So you still only get one hardware pin change interrupt per port, right? Per sort of 8 pins. You only get it on change. But what the very clever author of this code has done is says, okay, well, what I will do then is sort of enable these interrupts, and then when one of them is triggered, I will do some more thinking. I will look at the state of all these pins before the interrupt happened and after the interrupt happened, and then I'll be able to figure out which one changed and which one it changed, and then based on that, I could offer the user the opportunity to call different functions based on which pin changed, right? Which is a pretty clever thing to do, and it works pretty well. The reason that I want to come back to actually working with pin change interrupts proper in a little bit is, though this is very clever, it is of course somewhat slower than a genuine interrupt. The stat for interrupt running on the ATmega 32.8 is when an interrupt triggers, you will jump to your new code, I believe, in 1 clock cycle, right? So within 62.5 nanoseconds, you will be at your new code, because it's done basically in hardware. The software version, the interrupt enable library version of this, requires a lot more thinking before we're ready to run our code, right? So the process is essentially some pin changes state that we've told our library to look for. That will trigger a genuine hardware interrupt, but then a bunch more code has to run to check the states of all the various pins, figure out which one changed, figure out what the name of the function is and the address of the function is that the user wanted to run when that pin changed, and then jump to that function. It's just going to take a significant chunk more time before we get to that code. So though this is very powerful and very flexible, it's not going to be as fast as sort of manipulating the registers ourselves, but I wanted to put it out there because it does enable a lot of really cool functionality. We'll look at an example in the code here in a sec But you basically, when you've installed this library, you get this additional enable interrupt function that you give, sort of much like the attach interrupt function that's sort of native to the IDE. You give it a pin, you give it the name of your interrupt service routine, and you give it one of your many modes: falling, rising, or change. You don't get the low-level interrupts like you did with a genuine external interrupt, but rising, falling, or change are all possibilities here. So let's look at an example. This will be I have to load it up here, the enable interrupts example from enable interrupt simple, I think it's called, from the website if you want to play along. It's really just once you've installed that library, which again is linked on the website, once you've installed it, it's just the simple example from the Arduino IDE. So you go to File, Examples, Interrupt Enable, Simple. It basically pops up this. I took out some of the cruft just to make the example a little bit clearer for our case. But you're seeing it looks a lot like using a native external interrupt, right? We define a volatile variable, right? In this case, an integer, to be a count of 0. We say our interrupt function, our ISR, is going to be incrementing that count. It's going to look a lot like my example from earlier. We start our serial console. We attach a button as a pull-up, and we enable interrupts on a pin. When that pin is falling, we'll call our increment function there. And then once a second, we'll just print out how many times we've been interrupted so far. But what's cool about this is we're going to use a different pin. We're going to use pin 7 in this case, which is not natively a hardware interrupt pin on the Arduino, but this library makes it so. Let's do that real quick. So I'm going to come over here. I need to remember to rewire my button to pin 7, and we'll upload that code. While that uploads, I will bring this up. All right, so now, again, I guess there's not that much to look at over here because no blinky LEDs over here. So we'll open the serial monitor, and we'll see. I'll need to reset my baud rate to match this particular program. Clear that. See, pin was interrupted 0 times so far. But when I press the button, 1 time, 2 times, 3 times, 5 times. Yeah, so we still have our same debounce problem, right? There's no debouncing in this code. But the gist of this is now we're using a pin that is not a native hardware interrupt to do essentially interrupty functionality. I should clarify, when I say that the interrupt will take significantly more time to get to, we're talking in programming terms, right? So we're talking an additional, dozen or 100 clock cycles, so some number of microseconds, say. So in human terms, relatively fast. But if we're talking about, triggering an interrupt, say, in response to a 100 kilohertz serial signal, all of a sudden, a couple extra microseconds is the difference between our functionality working and our functionality running out of time to process before the next change in a pin. So it sort of depends what you want to do with this, but if what you want to do is respond to human human interface inputs like a button press or contact closure or a light sensor or something like that, this library is really cool to play around with. And it can basically do just about anything that a genuine hardware interrupt can do, just with the caveat that it will be somewhat slower. I will also plug the author of this library, the Enable Interrupt library, does a really nice job of sort of outlining the advantages and disadvantages of this scheme. Did some really cool timing experiments, figured out like how many clock cycles slower or faster this process is going to be. So do go check out the library and the wiki attached to it on GitHub, because it's a cool read, and it sort of shows the thinking about developing this software-based solution, and how you think about expanding on functionality that's built into the Arduino, while also sort of like being really clear about like, this is a cool thing you can now do. Buyer beware, it may be a little slower. Is this really the right thing for you? Palmer asked a really good question. Can you interrupt an interrupt? No. By default, no. When you run an interrupt, whether your own or somebody else's, by default, interrupts are disabled for the duration of that interrupt being called, which is one of the reasons it's so important to make your ISR short. You don't want to miss another interrupt coming in that really needs timely attention. We don't want to spend a couple milliseconds working on setting the state of lots of things or taking lots of readings, because we might miss another input or some serial input or something like that. So no, you cannot. There is a way so basically what happens when an interrupt is triggered, a flag is set, a bit is set that says we are currently running an interrupt, don't run any others. When the ISR is done, it will take care of resetting that flag to sort of re-enable other interrupts. You can re-enable that flag yourself manually within your own interrupt, but in my opinion, especially in a case in the Arduino where you have a limited number of interrupts, I don't know of a case where you would really be better off re-enabling those interrupts rather than just finding a way to shorten your interrupt so that timing wasn't as critical. In a computer programming environment, you have a more nuanced version of sort of interrupt hierarchy. So you can imagine, to make up an example, things that happen slow and fast. So an audio buffer, right? Thinking of Palmer, who asked the question, being an audio guy. You know, if your computer is playing sound like all of ours hopefully are right now, hope you can hear the sweet jams. If your computer is playing audio, it basically needs to update the analog level, the waveform table, to the output, the headphone output, the speaker output for your computers, many thousands of times a second. You know, say 48,000 times a second for a 48 kilohertz sample rate on your standard CD audio track, say, right? So 48,000 times a second, some program on your computer needs a little bit of time, just a little, but needs to be able to say, okay, I need the next 48,000th of a second of some data because I got to put it in my user's ear, right? And for a computer, right, that's running at gigahertz, right, being interrupted 48,000 times a second is actually not that bad. And this is a simplified example for it. This is not necessarily how actual audio processing works on a computer level. There's sort of more low-level processes than this and separate audio chips. But you can imagine, right, every 48,000 of a second, I need a little bit of time, says OBS or VLC or whatever you're using, to just update its data. So that's a relatively slow and relatively low priority process, but it has to happen with relative regularity, otherwise you start hearing audio glitching. The memory in your computer, the RAM, needs to be refreshed very regularly, or the ones and zeros in it will dissipate out of the capacitors that store them, and you will lose all the data in your RAM. That must be done with very high frequency, a relatively high frequency, on the order of I think 1,000 times a second, but it must be done. So modern computer architectures have this idea of a nested interrupt hierarchy, where, you know, if my computer is currently thinking about displaying how to display this pretty face, for example, updating the bits and bytes that make up the screen, and the audio program says, I'm throwing a software interrupt, I need a little bit of time to update my audio driver, the program will say, okay, no other interrupts for now, unless they're really high priority. Something like a RAM interrupt might come in and say, hey, I need a tiny bit of time, but I need it right now. And so you're able to sort of jump from a level 0 interrupt to a level 1 interrupt. And maybe another hierarchy higher than that. I think most, at least PC architectures, which is what I'm more familiar with, have 2 levels of hierarchy, maybe 3. But beyond that, it's just sort of you keep your ISR short and return them in time, and everything works out okay. That's the long answer to can you interrupt an interrupt. On the Arduino, by default, no. But you could re-enable them if you wanted to. I don't know of a good reason to want to. That's the answer I could have given you, but we're down nerd rabbit holes tonight. Let's see. So go check out the enable interrupt library. It's basically a way of generating fake hardware interrupts on other pins at the expense of time. So you could enable hardware interrupts on lots of different pins, right? You could say, I want an interrupt on pin 9 that calls function A when that's on a rising edge. I want an interrupt on pin 10, calls a different function on a falling edge. I want to interrupt on pin 11 on a change in pin. So you could have these, say, hooked up to 3 different buttons, right? So whenever I press this, the up button on my Nintendo controller, set a flag that says up button is pressed, and another interrupt for a left button and right button, and so on. And then later on in my code, I could say, okay, well, now when I have a little time to think about it, if the up button has been pressed in the last loop, then do something. The right button is pressed, do something else, and so on. You'd have this sort of interrupt-driven programming model where your program is basically just constantly looking at what the state that has been given to it is, and since all of your input is handled in interrupts, you would be sure you would never miss an input, for example. So an interesting way of thinking about structuring your program. A couple of little miscellaneous facts. interrupts will trigger on an output pin, right? Whether this is an external interrupt or a pin change interrupt, interrupts trigger even if the pin is configured as output, right? So when we look at an example like, enable interrupt on pin 9 when it's on a rising edge, that will be true whether I have a button attached to it that pulls that pin high, or I do a digital write pin 9 high. Excuse me. When that pin goes from low to high, no matter what caused it, we will trigger that interrupt. So this is a way, there isn't, a particular way in the Arduino environment to do software interrupts, like interrupts triggered by a specific place within your code, which may be a thing that you could want to do. You could want to have an interrupt that's triggered by a button press, but we might want to have the sort of ability in software to do exactly the same thing. You can do exactly the same thing just by causing that pin to undergo the same voltage change as if you had made it happen externally. So a little thing to be aware of there, that you can toggle these pins manually if you want to, or if you do toggle them manually, you will trigger any interrupts you have attached. And this is a little point I mentioned earlier. An interrupt that happens during another interrupt will still usually set this pending flag for that interrupt, but won't execute until the first interrupt ends. So if I have an interrupt on, say, pin 9, an interrupt on pin 10, triggered by a couple of buttons, let's say pin 9 interrupt triggers, I'm dealing with it over here, the user presses the button attached to pin 10, I'm still going to be running the code for pin 9, but as soon as it returns, I will jump to the code to handle the interrupt on pin 10. I'm not going to lose that flag, I'm just going to have to delay the execution of it. That is generally true. There's a couple of exceptions, but we'll have to wait just a little bit. Questions, comments, issues, concerns, things we want to play with or try. We're at a little bit of a branching point in the evening, so I'm going to take a sip of cider and take some questions and play with some. Nate's got a question. Let me read it while I sip. Brewery recommendation near Chicago Union Station. Oh, that's tricky. Union is downtown. There's probably a Rock Bottom near there, which is not super local, but it's pretty tasty. 6.5 hours. That is a haul. I'll let some of the beer heads in the crowd chime in. I know Chris is a beer aficionado. See if anyone has any recommendations. But downtown is a little bit tricky. You might be served by like just going to the local Binny's liquor store and finding a park. I think a lot of good stuff there. Feel free to jump in with other questions or suggestions for Nate on good Chicago beers downtown. Let's see, what was our next? Ah, great. So we're actually in wonder of wonders, miracle of miracles. We are basically through the content for tonight, and it has been a genuine 90 minutes, not a Jeff Glass 90 minutes. See, I told you I finally didn't get in over my head with the topics for tonight. Which does leave us room, like, I'm not going anywhere. We are happy to keep playing around with, like, possibilities and questions, but I know, Palmer, I know. I'm beside myself. But so I want to give you a little bit of a flavor of what's coming up the next 2 weeks and how it ties into what we've talked about so far. And Palmer, essentially, it related. One thing that you should have asked about, like what is a timer and what is the 555 related to interrupts. So I'm going to give you a little flavor of the non-hardware interrupt side of things that we're going to focus on in the next couple of weeks. So just to give you just like a little flavor of how timers and interrupts relate to all of this. We've referenced timers a few times before, right? I swear we're not getting into this as the topic for tonight, but just to give you a little taste, a little flavor. The ATmega328 has 3 timers called timer 0, timer 1, and timer 2 that automatically count up in the background at some fraction of the clock speed. So we said before, the ATmega328 operates at 16 megahertz. You would have these counters count up, 16 million times a second, or you can apply a number of dividers so they count somewhat slower, right? And you don't get a sort of infinite variability, but you can say, hey, I want this timer to count up at half the clock speed, or 64th or 256th of the clock speed. 16 megahertz is faster than I care to count. And the when I say count, timer 0 and timer 2 are single byte counters, so they count from 0 to 255. Timer 1's a 16-bit counter, so they count from 0 to 65, 535 before they wrap around to 0 again. And you can trigger a number of interrupts that you can sort of attach to various states of these timers. So if we go back to our datasheet here and look at our interrupt vectors here, we can see we have our, our hardware interrupts up at the top here, but our timers have a whole bunch of interrupts attached to them, right? We have our timer 2, timer 1, timer 0 interrupts. We get a couple of compare interrupts, so we can say, hey, when this counter is equal to a certain value, throw me an interrupt, right? I actually get 2 of them per timer. I get a comparison A and a comparison B per timer. I also get an overflow interrupt to say, when this timer reaches its maximum value, throw me an interrupt when it wraps around back to 0. And that's kind of neat because we can, like we say, control the speed that we sort of count up to our maximum value at. We also need one more sort of cool timer interrupt for timer 1, which captures an input. It gets triggered by an input state and captures the value of the timer at that time. It's really nice for making like sort of stopwatch functionality into your timers. We also have a few other software-based timers in here. Like I say, based on the serial port, the USART, the EEPROM, which is our long-term memory when that's ready to accept new bits, analog comparison, all that kind of good stuff. But the timers are really where it's at. So if I, the timers do a lot of the work for us under the hood. So a lot of the functions that we've already used have already been based on timers without us knowing it. If you think about a function like, set my timer to counting up to 255 and just sort of goes 0 to 255 and reset back to 0 when you get there. And every time your count is less than 200, set pin 3 to high. Every time it's more than 200, set pin 3 to low. That is essentially a analog write to pin 3. If we change the value at which our counter tells our pin to go from high to low, we can adjust the duty cycle of our waveform as that counter counts up at a consistent speed from low to high. The pulse width modulation is based on timers. Servos are based on timers. I'm so sorry. The tone function is based on a timer counting up at various speeds, all kinds of good stuff like that. So we've actually seen a fair amount of timer functionality already without knowing it. What we're going to do in future weeks is tap into how those timer interrupts actually happen and use them to be able to control our own code that's doing things at very regular intervals using the internal hardware of the Arduino. So which leads me into what we're going to talk about in the next week, on next Sunday, and maybe the Sunday after. So here's the confession. This week I feel very good about the amount of stuff that we've covered. Right? We're at an hour 40. I think we're good. We're digestible. Next week, I think I referenced before, we're gonna at least talk about registers, just bytes in the code, bytes in the processor that do specific things, that control its functionality, control its clock speed, inputs, outputs, peripherals, all that kind of good stuff. And the reason I want to devote a bunch of time to it is for 2 reasons. One is a lot of this information just comes straight from the datasheet, which once you know how to read it is really very straightforward and well laid out. But like, for example, here's a little snip from the datasheet here of the MCU control register. And if you obviously this is in context in the datasheet, but it's kind of opaque. Like it's a little bit just hard to parse what this is trying to tell you. So I want to go through some of the registers in the datasheet and show you what they mean and how they are accomplishing things that we already know how to do, so that this just becomes a much more readable process. And I want to take the proper time to learn how to digest what the datasheet is telling us. The other thing is, we basically said that individual bits of these registers, individual bits of these bytes mean something to the processor. The IV select bit means something different from the IVCE bit, means something different from the PUD bit, and so on. And so to work with individual bits within these bytes, the easiest way, the cleanest way, and the way that we'll be working with them is using some bitwise math. Basically, math that operates on individual ones and zeros within a number. Which again is once you know how to parse it, is really straightforward. But if you haven't run into it before and we haven't used it much, this is some examples down at the bottom of the screen there. It can be just a little bit tough to parse. So I want to take the time to go through what all the symbols mean and how they work and how we can sort of work with these bitwise functions to modify registers. And that'll just make this a lot easier. So that's where we're gonna start next. And then I'm not 100% sure if timers are going to and timer interrupts are going to be next week or the week after, to be perfectly candid, because I want to do really good I want to do a really good justice to registers and register math, and I want to show you how a lot of the functions that we know and love, like pin mode and digital write and analog write, are really just under the hood manipulations of these registers to show you that they're not scary at all. They're just are kind of written in an opaque way, and that's partly why the Arduino IDE is great. Is it takes a thing like, you know, DRD for left shift 4 bytes and or equals 1 and turns it into digital write pin 4 hot. You know what I mean? Like, there's cleaner ways to write this stuff. But once we understand how those two things match up, we can start getting into functions in the timers that we can really only accurately access through register manipulation. So we're definitely going to do that next week. We're definitely going to do registers next week. We may get into timers. I want to make sure that we leave enough time to talk about and play with registers, and we'll see how deep a dive that goes. Here's the links. They're in the slides. The slides are in the link in the description here. They're on the website. They are on, yeah, that's the two plain places that they are, I suppose. Ooh, Chris nailed Haymarket Brewery. Haymarket, great. Yeah, anywhere over in the like Fulton Market area, which is a little bit west of the loop there, would be really good. There's a really good, I don't know if it's open, but it's a really good fried chicken place there on Fulton Market. I don't know what it's called, but it's really tasty. Yeah, if you have 6 hours, you can do a really good fun time. Questions, comments, issues, concerns on hardware interrupts before we close it up for the night. I have 1 sip left. This is timed out so well. I'm so proud of my timing this week. I cannot tell you how many weeks we have gone when we've gone to like 3 hours, and that's just unsustainable. I mean, unsustainable, I mean, it's been almost every week, so clearly it's somewhat sustainable because we're still here. But I think in terms of, I think registers themselves could be a whole night, and since that's the next stepping stone, I didn't want us to get too into the weeds and try and be like slogging through, you know, bitwise Zor at 11 p.m. when our brains are all dead. Let's just start with basic hardware interrupts and their functionality, and that's I think a good place to leave it for this evening. Yeah. Thank you. Feel free to shout out questions as I'm gonna do the ending business because I can. But feel free to shout out the questions because, like I say, I can't believe how early it is. We're doing great. If you have questions, comments, issues, concerns, you can leave them as a comment on the website or find me on Twitter at JeffersGlass, which is, I always get the side wrong right here. If you like this video and want to be reminded when there's more, you can subscribe to this channel. I also am doing more videos on the Tiny Moving Light project, which is a lot of fun, which some of you may be here from tonight. I know it's a kind of a different topic here, but that is version 0.8 of the Tiny Moving Light project, and PCBs. This is the next video here. Your bonus for sticking around to the end tonight is to see the PCB version 0.81, for which there'll be a video, a slightly less produced video, I think, coming out pretty soon. That last one got a little bit out of control. This one was machine assembled by JLC PCB, which saved me just hours of time. I actually have a couple of them here. This one's fully assembled. This is how they come off the assembly line. Palmer, I have a the brand is Maker Select V2.1. It's one of the Monoprice 3D printers. It is a rebadge of the Wanhao Duplicator i3. They're literally the same. Mine just has a Monoprice sticker on it. I got it fall 2017. I want fall 2016. I have to go back through my blog. But yeah, that's where the state of the project is. So I'm hoping to just release a new video that's like a little bit less of a bear to edit and maybe with some better audio. Sometime in the next week and a half or so, just to share like the automated assembly process here, because it really, like, beforehand it was like, okay, this is a labor of love, but I can hand assemble these. I cannot believe that here in 2020, for like a relatively nominal cost, you can design a circuit board and have somebody else manufacture it to you and ship it to you. Like, I've been doing cost outs on like how much the unit cost would be per board if I were to do a mini bulk run, and it's astonishingly low. Like, I'm so excited about this project just because like the resources available to us as hobbyists are insane, and it's gonna be a lot of fun. So, but there's, you know, more modifications to do as well. I gotta redo the 3D prints, gotta do some more filing. I changed from like a threaded insert, you know, method of securing the lid to a press fit, and then try to do a tab, but the tab broke off. It's a whole thing. So more on that, I think, in a dedicated video at some point, but that project is coming along. I'm just having a lot of fun. And I gotta say, like, as much as I learned from these these nights, like, figuring out all the finicky details about interrupts and things so I can try and share them with y'all. This project, similarly, I have learned so much from, like, how to do automated assembly, thinking about part clearances, thinking about, current limits on traces, thinking about pricing out BOM. Like, it's been really cool to experiment with this kind of stuff. So that's been a fun learning thing. And things like that, I think I said this a couple weeks ago, but like, it really does incorporate a lot of the stuff we've been learning for the past 16 weeks. Like, very literally, the take your Arduino off of the Arduino and put it on a breadboard is exactly the same process that lets me program this Arduino controller via this header. And this is not an Arduino Uno by any stretch. Things about like current and power limits were helpful in like specking out this buck converter and this buck converter. RS-485 is the chip that's, the RS-485 converter is right there to receive DMX that we talked about just last week. Like, it really does feel kind of like things are coming together in a really cool way between these, well, Sunday nights most of the time and my own personal projects, and that's been really a joy in the last couple weeks. But yeah, it's cool. Cool things are happening. It's always good to see you all here on usually on a Sunday night, let alone a Monday night. This coming week we'll be back to our usual Sunday nights at 7 p.m. Central here on YouTube. The link will be on the website coming up in advance. All the slides and the code will probably be up next Saturday or Sunday. That's usually when they go up. Do check out these links in the slides. They're pretty fun. And do go play around with Godbolt. Go around and play with the Compiler Explorer, because I think it's a really good way of trying to like get your head around what happens when you turn your code into code that can be written and run on an actual Arduino compiler. Thank you all for spending this time with me. I really do enjoy it. I hope it is, as always, I know it is a privilege to be able to spend this much time away, and I'm grateful for it. I hope you are too. I hope you use this as an opportunity to draw strength from these nerdy things that we do together to go out and make the world a better place. Please keep safe, keep separate, keep washing your hands, keep wearing a mask. You are all great. I want to see all you nerds at a bar when we can actually build things together in person. This is awesome. But I'd rather see you over a cold frosty beer at the same table, and let's get to that point as soon as we possibly can. You are all swell. Thank you so much, and I will see you next Sunday night to talk about registers and maybe timers if I get it over my head. We'll just see what happens. Thanks, y'all. Have a great week. Night, Chris. Night, Palmer. Nate, good to see you, Rufus Doofus. You take care of yourself out there, and I will see you next Sunday.